Okay. Good. So I think we can start. We're going to have a brief session of updates and description of the Cambridge ELLIS Unit, and then we are going to proceed with the talk by Mark. First, for those of you that haven't heard about Cambridge ELLIS Unit yet, this has been a new unit built within the ELLIS network, and the goal of the Cambridge Unit is to build on this excellent machine learning and AI infrastructure currently present at the University of Cambridge, and to promote research excellence and accelerate research. Our goal is to attract outstanding people that will serve as talent magnets. It's going to be at all levels, from PhD students, postdocs, faculty. We want to produce world-leading research in machine learning and AI, and to train the next generation of machine learning experts. And finally, we are going to be engaging in different aspects to help society benefit from AI. We plan to get involved in the startups, participate in secondments with companies, and so on. Who are the current members of the ELLIS Unit? We have a diverse group. We have Bill Byrne. He works on machine translation at the Department of Engineering. Gabor Sani, he works on machine learning with applications to molecules. Subin, everyone probably knows Subin. He's currently affiliated with Google. It was on the news today because he received a Turing World Leader Fellowship. So yeah, he's part of the ELLIS Unit. Mark is here with us today. I will give a brief intro to him before his talk. We have myself, Anna, who is works on natural language processing. Neil Lawrence, he's in the computer lab. He works on probabilistic machine learning. Carl Rasmussen, everyone knows him. He has a lot of experience of Gaussian processes and applications of these methods in reinforcement learning. Michaela, she's an expert in health, machine learning applied to health. Rich, he works on probabilistic machine learning with applications to learning, computer vision, and other aspects. Adrian Weller, he works on robust machine learning, interested in fairness, interpretability, and so on. Eiko, she's interested in applications of machine learning to computing systems. And then we have Christian. He's an affiliated faculty member, and he's one of our main contacts for interactions with companies. I'm very happy to announce that we have an administrator that we have recruited recently, Kimberly. Kim. She's going to be in charge of basically running the ELLIS Unit, and she's going to be helping a lot setting this up. There are more members of the unit that will be added in the next months or so. Pietro Rio, he's a fellow of ELLIS, Ferenc Husar, and other people that are doing also great work in machine learning at the university. Some updates on the ELLIS Unit. We have some new ELLIS students, in particular, Javier Antoran and James Allingham. They have been accepted within the ELLIS PhD program. They will be doing visits to different ELLIS units in Europe. Sreya Spadi is a new PhD student, also accepted into the ELLIS program that he's going to be joining this year. Javier and James, they will be visiting the ELLIS unit in Amsterdam. I think it's in the next months. Javier is going to be working with Max Querin, and James is going to be working with Eric Nalinsky. We have submitted recently a research program with a focus on machine learning for molecules, and we'll see if this is accepted. We are very positive on this. There are members of the ELLIS Unit, the Cambridge ELLIS Unit, that are already involved into different research programs from ELLIS, like ELLIS Health, this research program on robust machine learning, human-centric machine learning, and so on. We have almost a new website ready. We are giving the ultimate details on this, and this will be available very soon. We are planning to organize some events, like, for example, machine learning winter schools that will happen probably close to Christmas or shortly afterwards. And finally, just to describe a bit of the amount of research work that has been done by members of the unit, if you count the number of papers that we published recently, this amounts up to 100 papers published, most of them in top journals and conferences. Good. So this is all from the unit. I don't want to take more time. I will stop sharing this, and I would like to present now the speaker for today. Maybe Mark, if you want to start sharing your slides, you can already do this. So let me give an introduction to Mark. He's a chair of civil engineering. He holds the Royal Academy of Engineering research chair in data-centric engineering. His research lies at the intersection of statistical, mathematical, and computing sciences. And he has been the founding executive director of the Alan Turing Institute, and currently is program director in data-centric engineering at the Institute. He has been elected fellow of the Royal Society of Edinburgh. He was an EPSRC Advanced Research Fellow, an EPSRC Established Career Research Fellow, and he has received a Royal Society Wolfson Research Merit Award. He advises also the government from the UK in areas related to machine learning and AI, and he's editor-in-chief of Statistics and Computing. And today he's going to talk about the statistical finite element method. Thanks a lot for joining, Mark, and you can go ahead.
And thanks very much, Jose, for the invitation to come and speak. It's really exciting to be involved with the Ellis Cambridge unit, and I'm very much looking forward to seeing how things develop over the next couple of years. So what I'd like to talk about today is something, is a piece of work that really sits at the intersection between applied mathematics, machine learning, statistical science, or computational statistics in particular, and various application areas. And this is entitled the Statistical Finite Element Method. And this work, of course, progresses with quite a large number of colleagues at Cambridge and at the Alan Turing Institute, who of course come from various universities across the UK and Europe. And in particular, a number of colleagues from the University of Western Australia in Perth. So what I want to do this afternoon is introduce you to the finite element method. I'm going to give you a whistle-stop tour of it and of the foundations, the mathematical foundations of the method, but highlighting the practical applicability of it. And I'm then going to highlight some of the shortcomings of this methodology, this applied mathematics methodology, especially for the age that we currently are working in, which is very much data-centric and data-rich. And so what we're going to do is we're going to take the finite element method and we're going to reconstruct it within a statistical framework. And the first thing that we will do is we will define a reference probability measure. We will construct a reference measure in the Hilbert space of functions that are solutions to the partial differential equations that we're interested in. And once we've been able to do that, then of course, the combination of the finite element representation and observed data is something that's very natural, and it's something that comes with all of the statistical consistency and coherence. And what I'm going to do thereafter is just give you some brief examples of real world big applications that are currently being run using this statistical FEM method. We'll be looking at a bridge, a railway bridge that's operated by Network Rail, and how we're able to monitor that in an automated and remote manner. And then I'm going to very briefly present an extension to time-evolving systems, time-evolving nonlinear systems, and look at two things in particular. One is the modeling of solitons, which are subsea waves, and then very briefly look at some reaction diffusion dynamics as well. But I'll run through it reasonably quickly so that there's some time for questions or discussion. So what is the finite element method? Well, it's basically a numerical method that allows us to solve partial differential equations. And if I look at the textbook example, so anyone who's studied the engineering tripos here will have met the Poisson equation. So the Poisson equation is typically defined on some spatial domain. So the domain in this little example here is a square, and the interior of the domain is denoted by omega, and the bounding of the domain, so the bounding area, if you will, is denoted by a delta or partial omega. And within the domain, a partial differential equation will be satisfied. And this partial differential equation is one that most schoolboys are familiar with. So this is the divergence of the product of this tensor here, this diffusion tensor here, A, which is a function of spatial location and then certain parameters. So it's the product of this diffusion term plus the gradient of the function that we're interested in. So U will be some function of the coordinates in the domain. And the equality on the right-hand side will be some forcing. And so this equation here is basically a diffusion equation. It's a steady state equation, and it would describe, for example, the temperature profile in this little square here at steady state. And then the boundary, on the boundary, what we're saying is that the value of the function that we're interested in that would satisfy this partial differential equation is set to, in this case here, 0. So the function value is 0 on the boundary, and within the actual domain itself, then the function would be such that it satisfies the Poisson equation at every interior point. Now, of course, this isn't terribly interesting because it's just a square box, but the beauty of this particular methodology is that we can take any arbitrary shape in the space that we're actually interested in, and we'll see some examples of that just shortly.
Can I ask one question quickly?
Yes.
The output of the function, what's the dimension?
So in this case here, the function, in this case, I'm just saying that it would be just a scalar, so we would have some field, but it would not necessarily be a scalar. It could be vector valued as well. So you could have a vector valued function.
Okay, thanks.
Okay, in the most general case, but I'm keeping it simple for the purposes of notation more than anything else. Okay, so what do we then do? Just let's remember that for most, in fact, for the Poisson equation, if we have some arbitrary bounding domain, then there is no analytic solution for something as straightforward as the Poisson equation. So what the finite element scheme does is it posits a space of functions which in most cases will coincide with the space of functions of the solution that we're interested in. So we will take functions v, which will be in elements of some Hilbert space, and in fact it would be a Sobolev space in this case here. So each function would be an element of H1, where H1 would have finite valued metric, which would comprise of the function itself and its first derivative. And the values would be 0 on the boundary of the domain. Okay, so we have these, what we would call testing functions, drawn from H1 and whose values would be 0 on the boundary. And what the first thing that we do is we define what is called the weak form of the partial differential equation that we're interested in. So we will take the Poisson equation, we will multiply both sides by the test function v, and we will integrate both sides over the domain omega. And if we do some schoolboy integration by parts, then what we see is that the left-hand side looks something like this. We have this integral of the product of the diffusion tensor and the gradient of the function that we're interested in. And we take the inner product of that with respect to the gradient of the test function, and then we integrate. And on the right-hand side, you can just see the inner product of the forcing function, whatever that is, and the test function. Now, what's interesting here is that we have immediately relaxed the conditions required in U. You can see that the original PDE requires that U would have to be twice differentiable. The weak form, however, basically requires that the value of the function, the functional form, just has to be 1 times differentiable. So immediately we're relaxing the constraints that are required on the smoothness of the solution class that we're going to be interested in. Now, the main point of all of this is that what you can see here is that this is basically a linear form which takes inputs the function of interest and the test function. And so we can just write this in operator form as calligraphic A, whose inputs are U and V, U and V being the functions, and some set of parameters that characterize the overall differential operator, lambda here. And on the right-hand side, of course, we just have the linear form of the inner product. Now then, what follows is that we take a subspace of the infinite dimensional space V, and we'll call it V sub H, such that V sub H is spanned by a finite set of basis functions. So in this case here, we're saying that there are m basis functions that span the subspace V sub H of the overall function space, the overall Sobolev space that we're interested in, V. And if we then take this weak form and note that elements of V sub H will be written in terms of a linear expansion of the basis functions, it then means that a finite dimensional approximation of the function of interest can just be written as a linear weighted combination of the basis functions that span the subspace. And so in the finite representation of this bilinear form, we basically are now going to have a set of an n-dimensional set of linear functions. So we have this linear system in the basis functions phi j. And what that means is that we can now estimate or approximate the actual weighting coefficients of the basis functions, which go to define the approximating function. Now, the key thing about this FEM method is that we can partition the domain in a finite way using a set of basis functions. So the first thing that is done, I'm not going to go into the details, but we can subdivide the domain into elements, hence the name finite elements, because we've got a finite number of discrete elements that partition the space. And now if this was an arbitrary domain, then it would partition a subset of the domain. And what you're seeing here is a set of elements which are basically just triangles. So we have these finite triangulations which cover the domain. And within each of these triangulated elements, there will be a particular node. And on that node, we would then apply a basis function. So there would be these nodal variables. And that is how the basis is introduced onto the actual space that we're interested in ensuring that the PDE of interest is satisfied. So that's how we partition the space. There's quite a lot of details about overlapping and so on, but I won't go into those details. I think suffice to say that we basically take some simple geometric elements and partition the space in a non-overlapping manner. And on each of those elements, a basis function will be placed. Now, what we'll do is we'll say that the characteristic length of the mesh that we've now created is h. And you can see here for this very simple uniform mesh here, h would just be the length of each of these triangles. So that would give the characteristic size of the mesh. And what it means that we can then do is that we can interpolate locally to define the actual function values on every possible coordinate point in the space. So although that we have defined the function values at a finite set of nodal points, we can use simple interpolation to actually obtain what the function values would be where there are no nodal points. So this is quite nice and probably very familiar to you for those of you that are familiar with function approximation schemes. Now, what's interesting is that if we look at the analysis, we see that the convergence and the rate of convergence of the finite element model approximation to the actual infinite dimension function. So in L2 error, it will converge at a rate of h squared, where h, of course, is the size of the element. So we can see that there is a nice consistency in terms of the rate of approximation of this methodology. And you can see here clearly that the type of function and its smoothness is also going to impact on the rate of convergence. And so there's a lot of analysis that's been done on characterizing the theoretical properties of this methodology. But I think what's really exciting is the way that this methodology has now been developed and is widely used in just about every area of the physical, the chemical, the biological sciences, and in just about every area of engineering that you could imagine. And I've just given some examples here. So this is a rotor of an electrical motor, and what you're seeing is the finite element solution describing the flux lines and what the flux densities within the material and within the actual component happens to be. Down here, you can see a very complex structure. And again, the finite element method can solve numerically partial differential equations, in this case, describing the elastic or the plastic deformation of this very complex structure. And it can do it in a very elegant manner. And so you can see here, the areas where the stresses or the potential strains are actually quite high and where they are actually quite low. And just to emphasize the sort of arbitrary nature of the geometries that one can deal with, here is a jawbone. So the domain omega is this very complex 3D shape, and the equations of mechanical deformation, so stress and strain, the equilibrium equations and compatibility equations, the partial differential equations describing all that, can now be solved for any type of forcing that's applied to this jaw. So it's really a technique that has got very rich theory, that has very strong and powerful computational tools that allows us to deploy it in the study of, as I said, lots of different types of physical, chemical, biological systems. So it's very exciting, and it's hugely effective. However, I want to burst the bubble here. The thing is that we know, and in machine learning we know this very well, is that models and mathematical models are in essence idealized representations of whatever the physical reality happens to be. So they are idealizations. In some cases, these idealizations are very close to the sort of truth, but in many cases, they can be mis-specifications of the truth, and in some cases, highly misspecified representations of the reality that we want to understand. And so immediately, we now have an uncertainty, an inherent uncertainty, just by writing down a partial differential equation. So there's one thing, we now have uncertainty. And that uncertainty could be in the PDE. It could emerge because we don't really know what the forcing function is like, or the constitutive laws describing the material from which, in the diffusion case that I just gave you, just exactly how this diffusion tensor is characterized. It may well be that our boundary conditions are uncertain. The geometry of the domain may be uncertain, may be poorly characterized. And indeed, some of the physics, some of the chemistry may actually be missing or just poorly specified. And so the question that also arises in a data-rich age, where we can now pretty much instrument most most things that we come in contact with, and therefore gather data on them. How do we deal with that data, and how do we assimilate that into our finite element model, and therefore how do we update our model in the light of that data. And so what is really missing in the finite element method is a way of characterizing all these mis-specifications and indeed assimilating data. And so that was really our motivation for the definition or the redefinition of the finite element method. And the way that we did it is that we, rather than taking a very classical function approximation in a Hilbert space setting, is that we said, well, we'll still be working in Hilbert Hilbert spaces. But what we now want to do is we now want to endow that space with a probability measure, which will then allow us to represent the finite element method using a probability calculus. And once we have that, we can then basically open up the statistical toolbox and use all of the statistical tools that are available to us. Whether that is hypothesis testing, whether it is computing marginal likelihoods to see just how good the model happens to be, and so on. So the very first step was to define, in classical terms, what we would call a reference probability measure in the solution space, in the Hilbert space. Now, it's well known, and in fact, in the course that I teach in the engineering tripos in 4M24, we show that the standard reference measure that we all know in machine learning, when we're working in Rn, which would be Lebesgue measure, as soon as we go to a Hilbert space, an infinite dimensional Hilbert space, then Lebesgue measure is not defined, right? There is no definition of a measure that has the properties of Lebesgue measure in a Hilbert space. But there has been work that shows that one measure that is well defined in an infinite dimensional space is the Gaussian reference measure. And for those of you who study Gaussian processes, another way of looking at the Gaussian process is to consider it as a measure, a reference measure in a Hilbert space. So the other view, rather than looking at it as a measure on a stochastic process, one can look at it as a reference measure on the function space, the Hilbert space in infinite dimensions. So if we posit such a Gaussian reference measure, then of course it means that by the use of the radon-Nikodym formulation, we can then start to think about taking or defining probabilities of data based on the fact that we have this measure in the infinite dimensional Hilbert space. And people such as Larkin in the late 60s and early 70s constructed Gaussian measures in Hilbert spaces. And then more recently, Andrew Stewart looked at inverse problems in Banach and Hilbert spaces and focused on the construction of Gaussian measures as either priors, and in machine learning, we would recognize that as the Gaussian process prior. And in applied mathematics, it would be considered as the sort of reference measure for all push forwards from that reference to whatever other measure or conditional measure one is interested in. So the question then is, how do we construct this prior where it is embedded within the finite element method? So if we think of the weak form of the Poisson equation, and we consider a stochastic forcing, where the stochastic forcing itself is defined in a space that has some Gaussian measure associated with it, and we take a spectral expansion of the function of interest, u of x. Okay, so this will be an infinite dimensional spectral expansion. Then what we can see here is that the Gaussian measure on the forcing immediately gives us a push forward measure onto the spectral coefficients that weight the bilinear form acting on all of the spectral basis functions. And what that does, because of the linearity here, means that it induces a Gaussian measure on the infinite dimensional set of coefficients. Now then, now that that's well defined, we can then, in similar manner to the construction of the deterministic finite element method, is that we can use a projection operator and project from the original infinite dimensional space to the finite dimensional subspace. And in essence, all that we're going to be doing is truncating the infinite series. And what we end up with then is exactly the same as we have in the deterministic finite element method. But now what we have here is a push forward, which induces a Gaussian law on the finite number of coefficients of our expansion, which looks something like this. And for those of you that work in Gaussian processes, this will be very natural to you because we have this, in essence, this Gaussian process, if you want to think of it in these terms, whose mean, it looks like this. So this would be the mean function and then this covariance function. But what's exciting about this is that the mean function here happens to be the Gagliorcan solution of the finite element method. So in the deterministic case, what you in essence do is you construct this matrix here of the bilinear, the pairwise bilinear forms, and this is commonly known as the stiffness matrix. And B, of course, is just going to be the values of the inner products defined by the forcing function and each one of the basis functions. And then G is basically a convolution over the covariance function and the corresponding basis functions. And this is really nice because if you think about this GP here, one can think of this as a prior. And it's a prior that in terms that are quite exciting within machine learning is that this is physics informed. So all of the physics captured by the differential operators in the partial differential equation are now codified in this covariance function here. So the physics that is described in the PDE is now captured in this covariance function, and it's also captured in the mean function as well. And if we then select the basis functions to be finite element basis functions, then immediately we arrive at what we've called the prior or the reference measure for the finite element method in a measure or a statistical framework. Now this is, as I said, this is really quite exciting now because, again, for most of you that work in probabilistic machine learning, will immediately see that you now have a prior, and as soon as you start to obtain data, we can now update this prior. And if I just give you a very quick example, very simple example of the Poisson equation just in one dimension, so the domain is just the unit line. We are going to assume that the diffusion is just constant, that it's known. And what does the prior look like that's defined by this PDE here? So again, let's just remember that the prior is going to inherit this physically motivated covariance structure. And of course, here's what we've got. So we have the mean, which is exactly what you would obtain from Gagliorcan projection methods. But of course, we now have the additional information induced by the covariance structure. And so you can see that the boundary conditions are satisfied, and of course the uncertainty will start to grow as it gets to the extreme point from the data, and then it will start to shrink again as it goes to the other point where the value happens to be certain. Okay, so this is all good. We can then start to put a bit more texture onto this. We can consider more sophisticated cases where now the diffusion itself is a function that perhaps follows some constitutive material law. And again, if I just go through, I won't bother with the details, but now what you can see again is that we have randomness in the diffusivity, and that randomness is pushed through to the actual solutions that we would obtain. So again, if we focus just on the deterministic finite element method, we would just have this single value here, but of course we have a full probability distribution characterizing the variability induced by the fact that we've got this random diffusivity defining the differential operator. So this is all very nice and pretty cool. What is the analog to the classical convergence analysis, where we are just thinking of the approximation of the function in the space? What is its rate of convergence? Does it converge? Now, of course, we're no longer just working with the elements in the function space, the classes of functions. We are now working with the measures that are associated with that space. And so the question then is, in terms of measure, how does this prior converge? So how does the statistical or the probabilistic finite element method converge? Now, I won't go into the details. I'll just cut to the chase, I think. But the main technical issue, of course, is that there is no prior guarantees that the measures, the probability measures associated with the subspace V sub h, which is where our approximate functions will reside in, and the original Sobolev space, where the functions that we're trying to approximate actually reside. There's no guarantee that those measures would be continuous and absolutely continuous with respect to each other. It may well be that they're mutually singular, and we just, there are no guarantees of that. And so what that meant was that the sort of standard analysis that we would follow using either Hellinger distances or divergence distances or Kullback-Leibler divergences can't really be used. So the analysis that we conducted was based on Wasserstein 2 distance. And again, cutting a very long story short, what's nice is that the Wasserstein 2 distance between the classes of measures on the original function space and those on the approximating space, that distance will contract at a rate of order h squared. So in other words, we inherit the same consistency as we obtain from the classical finite element method. So we know that our measures will converge at that sort of similar rate. So this is nice, and is comforting that we have a methodology which at least is consistent in terms of the amount of computational effort that we could throw at it in terms of making the mesh fine. Okay, I've got another 5 minutes. Combining with data. Well, I'm talking to Ellis machine learning people here, and I don't need to labor the point that as soon as we've got data and you have this, we'll call it your Gaussian process prior, combining data is absolutely straightforward. So, you know, if I just think of a data generating model, we have our data and we have some projection operator which projects the finite element solutions, so the nodal points in the domain, to the points where measurements are actually made in the domain. We have some mis-specification error and we have some imprecision caused by measurement. You all know the drill. I won't bore you with the details, but the key is that this is really wonderful. This is machine learning 101 or Bayesian machine learning 101. The key here is that this prior is now defined by, again, the physics, which informs the mathematical PDE, which informs the finite element construction. This is our data. And immediately, we now have a way of updating our finite element solution in the presence of data or evidence. And this is now really important because as soon as we have mis-specification, and as soon as we admit we've got mis-specification, we can now use data to update whatever the reference measure based on the mathematical description it led us to. And we can do this in the typically coherent manner that we're all familiar with. So we have a statistically coherent way of combining the prior physical assumptions or physical knowledge with the observed data, and it allows us to take into account model mismatch. And we can do lovely things like work out marginal likelihoods and use Bayes factors, or if we don't want to be Bayesian, we can do hypothesis tests and so on. Now, I've just shown you the case for linear PDEs. For nonlinear PDEs, then things get a bit more technically involved, but the machinery is the same, and I won't go into the details, but again, most of you will be familiar with this. What I'm just going to show you, just to wrap up in the last 3 minutes, is an example where we do have a mis-specified model. So we have a true process that generates our observations, and then we have our posited mathematical model, which we encode in the PDE, and which we approximate using the finite element method. And if we just stuck with the finite element method, then we would have something that looks like this as our solution. But because we've got data at various and multiple observations of data at various points in the domain, you can see that by updating our finite element model with the data, we can now compensate for that mismatch. So this is a very nice way, and this is a good example of where physics-informed machine learning can actually be really powerful. Now, let me just finish off by giving you some real examples. So this is a bridge up in Staffordshire that's operated by Network Rail. Trains run over it. And our team here in Cambridge, when it was getting constructed, embedded a network of fibre Bragg sensors within the concrete when it was being poured. And so every time a train goes over it, or every time we want to, data is produced. So this structure is producing data all of the time. Now, of course, we can define a finite element model, but what's more exciting now is that we can define a statistical finite element model, and we can couple the two together using the strain data that comes from the physical device. And so any mis-specification in our model can be updated and accommodated by the data that we obtain from the actual physical entity itself. And this is really quite exciting. And again, it's subject to quite a lot of investigation, and it's something that's actually being used by Network Rail because it now allows them to remotely monitor the performance of this bridge. And I think this is a real, a very exciting thing that we can do with machine learning and applied mathematics. I mentioned to you time evolving nonlinear systems. We've done work on very complex systems. Again, I won't go into the details of how we deal, how we push forward the measures, how we assimilate the data in time evolving systems and time evolving nonlinear systems. But again, you would find an awful lot of the machinery that we use or emerges from this is very natural in terms of machine learning, using extended Kalman filters and ensemble Kalman filters and so on. We've looked at these solitons, these what are called rogue waves. And again, the key thing is that incorporating the data and updating the statistical finite element solution enables us to get more realistic predictions of how the waves will actually evolve over time. We've also been working on reaction diffusion processes. Again, I won't go into the details. And furthermore, in terms of going and scaling this up to finite elements where we've got millions of degrees of freedom, there are very nice computational statistical techniques using overdamped Langevin methods to propagate the uncertainty. And again, we've got some analysis that shows the sort of finite time divergence between the approximated measure and the actual measure that we're interested in. So this is taking these unadjusted Langevin methods. Again, I won't go into the details, but this is some more new work that's going on to really scale this methodology up. So let me just conclude by saying that what we've achieved is being able to synthesize data coherently with finite element models, and also accommodate the fact that the finite element models, based on the mathematical descriptions, may well be misspecified, and we can accommodate, or we can deal with that misspecification in consistent manners. And the sort of ongoing work, well, there are lots of applications, that very exciting applications that we're working on, but from a methodological perspective, scaling this machinery up to millions and tens of millions of degrees of freedom is the one that's really our focus of attention at the moment. And so there's a couple of papers, if your interest has been piqued, one that appeared just at the tail end of in fact, the beginning of this year in the Proceedings of the National Academy of Sciences, and then another one in a more traditional engineering journal. So I'll stop there, and I'll hand back over to your chairman.
Mm-hmm. Good, thanks. Thanks a lot, Mark. Really exciting talk. And we have some time for questions. So if anyone has any question, please just write something in the chat. I will start by asking some questions. I find this really exciting. And my question is about what was done before this approach. I think I mean, having the ability to combine this finite element method with observations and data is quite remarkable. Was this done before, maybe using any other techniques that didn't involve this probabilistic view of the finite element method?
So there have been stochastic versions of the finite element method attempted in the past, and basically what the approach was to take the spatial domain and then increase it by including a probability domain. And that then increased the size and the complexity of the problem. It wasn't terribly satisfactory. It certainly wasn't terribly scalable. And in terms of incorporating data, so if you think about it, a classical inverse problem where there's an underlying PDE in there would be using data. But what it doesn't do is it doesn't take into account the fact that the model itself could be misspecified and that data would have information about that misspecification and can therefore consistently and coherently be used to update the model. So, this is the first time that it's really been done, and I think that's why it was published in the Proceedings of the National Academy of Sciences, because of the potential impact that it would have, and because it was the first time that it's been done from the ground up in a kind of theoretically consistent manner.
Good, thanks. We have one question by Ed Stacy. He's asking, could this be applied to chaotic systems, for example, weather prediction?
I mean, the answer is yes, and it is, being used. One of the the model, the soliton model that we use is actually chaotic. It exhibits chaotic behavior, I mean, the answer is yes, and it's actually quite interesting because the value of information and the value of information and data for chaotic systems becomes a little bit more challenging, shall we say. But the answer is, yeah, if there's a system of partial differential equations and there's some domain and there is data, then yes, this could be easily used. And so we've actually been working on again some other chaotic systems. In fact, in the PNAS paper, we had the Kuramoto-Shivashinsky model, which is basically an idealized model of flame production, and it's a chaotic system.
Good. Maybe I can ask another question. So now that you have this probabilistic approach, and then you can also combine with observed data, you can also do any form of hyperparameter tuning, like, for example, the kernels that you're using in the Gaussian processes or so. Yeah. And my question is, have you found any? I can imagine that people were using maybe some default kernels or some default parameters for this finite element method. And have you found, for example, that this allows you to find values for those hyperparameters that are significantly different from what people were using, for example?
So yes, absolutely. There are hyperparameters associated with the kernels, and what we have been doing is just putting them in as parameters as they would be, parameters of say the diffusivity coefficients and so forth, and we've actually been taking a Bayesian approach, so actually getting the distribution over those and then just numerically integrating out. So it's not, it's just the usual overhead that there are hyperparameters, and depending on how you want to deal with them, whether you want to take a full Bayesian approach, or as we've just recently been doing, we're writing up a paper where we've also looked at, as you would imagine, variational approximations for this sort of construction. And then in that case, actually using an optimization to optimize the hyperparameters.
Mm-hmm. Good. We are out of time. Before finishing, I would like to, yeah, let me just stop your sharing. I would like to, let me see. Yeah, I would like to conclude by thanking our sponsors from the Cambridge ELLIS Unit. I think you can see my slide. Is that right? Yeah. So we have sponsors, and we are really grateful for the contribution towards running the unit. And thanks a lot for this. And thanks everyone for joining, and to you, Mark, for giving this amazing seminar. Thanks a lot.
My pleasure.
Bye, everyone. Bye. Bye-bye.
Bye-bye.
Thank you.